Hi class, in this video here we're going to move into section 2.1 talking about using first derivatives. So everything we learned in chapter 1 about taking the derivative of a function. First derivatives to find maximum minimum values in sketch graphs. So basically what this whole section is going to be about is, and future sections, is going to be about applications of the first derivative. And eventually we'll see applications of the second derivative. I'm going to break this lecture into 3 videos here. The first video is going to be the one you're watching now, is going to be like an introduction to the theorems and a very, very simple example to walk us through the theorems. And then the next 2 videos will be just examples. Okay, so the first thing we want to talk about is something called increasing and decreasing functions. So a function f is increasing over I, so I is some interval. All right, for every a and b in that interval. So if we have this interval that goes from a here to b over here, all right, for every value of a less than b, okay, f of a is less than f of b. So basically what this is saying is, look, as you increase x, as you move to the right, the function or the graph is going to go upwards. Okay, so as you move to the right, the graph goes upwards, the function increases. So the flip side is decreasing here. So function f is decreasing over some interval I if for every a and b. This a and b again is in the interval here. Okay. If a is less than b, when you plug a into the function, it's greater than f of b. Okay, when you plug b into the function. So a function is decreasing over some specific interval if as you move to the right, so as you move to the right, the function goes down. Okay, which is exactly what you would think. So a function is increasing over some interval if as you go to the right, the function goes up, and it's decreasing over some interval if as you go to the right, the function goes down. All right, so let's take this function here. So let's consider, this will be the first very simple example we'll drive home this thought process with. So consider the function f of x is equal to x squared. Okay, my first question is this. What intervals is the function increasing or decreasing on? So there's this belief right there, or this incorrect thought to say, well, the function is going up. Look, it's going up, so it's increasing across the real number line from negative infinity to infinity. So let me just say that this is incorrect. That it's increasing from negative infinity to infinity. Okay, that would be incorrect. All right, so just remember, as you go to the right, so as you move to the right, okay, what happens to the value of the function f? Look, as I go to the right, the function is going down. So it looks like from negative infinity until you hit 0, as you increase x, as you go to the right, the function goes downward. Okay, so what's really correct here is the function is actually decreasing from negative infinity to 0. And then look, after you go 0, as you go to the right, the function starts going up, and that it's increasing from 0 to infinity. And notice how I have open brackets here. I'll talk about what happens actually when f of x, what happens to how we classify when x is equal to 0. You'll see that in a later theorem here. But it's real important to know, just because the graph is open, a parabola that's opening upward, it's still decreasing from negative infinity to 0 because you go down as you move to the right. And then from 0 to infinity, it's increasing because you're going up. Everything goes from left to right. All right, so how can we use a little bit of calculus here to make this easy instead of looking at a graph? So if f is differentiable over some open interval I, we have the following, or let f be differentiable over some open interval I. If the derivative f prime of x is greater than 0 for all x in that interval, then f is increasing over the interval. And if f prime of x is less than 0 for all x in that interval, then f is decreasing over that interval. Okay, so really what's going on here, if f prime of x is positive over the interval I, it's increasing over I, over that interval. And then the same kind of deal over here. If f prime of x is negative over the interval I, well then it's decreasing over I. And let's go back to our simple example and show that, okay? So here, we have our function f of x is equal to x squared. We know that f prime of x is equal to, if you just take the derivative of this, it's just 2x. Well, look, here's what we said. We said it was decreasing over negative infinity to 0. All right, well, look, f prime of x is less than 0. And if you plug any number between negative infinity and 0 into the derivative, you'd be plugging a negative number in. So it'd be 2 times a negative number. So look, the first derivative is negative over this interval. So yeah, it has to be decreasing over that interval. And same deal here. It's increasing, what we said, over the interval from 0 to infinity. Well, look, f prime of x is greater than 0 over any value that you pick between 0 and infinity, okay? Because, it'd be 2 times a positive number, so it's positive. So this the sign of the first derivative, what I'm hinting at here, or what hopefully you're seeing, is the sign. So if it's either a plus or a minus of the first derivative, can tell us if the function is increasing or decreasing over an interval. Okay. Next, what we have, if you noticed going back here, I never said, what happens when x is equal to 0? Like our interval always goes from negative infinity to 0 and then 0 to infinity. But like what's going on when x is actually equal to 0? So this is what's called a critical value in the case of our example. So a critical value of a function f is any number c in the domain of f for which the tangent line at c f of c is horizontal. So that means the tangent line is equal to 0, or which the derivative does not exist at that value. Okay, so that is, c is a critical value if f of c exists, and so f of c does exist, but the derivative might not. The derivative is equal to 0, or the derivative does not exist when you evaluate at x is equal to c. Okay, so just if it's not clear here, this is all evaluated at x is equal to c. So look, if we go back and consider this function here, right? Does f of x have any critical values? Well, look, f prime of x is equal to 2x. The derivative is equal to 2x. Well, going back, a critical value occurs where the first derivative does not exist. So there's no values here that will make the first derivative does not exist. But you can find where the first derivative is equal to 0. So what this means is we have a critical value at this x is equal to 0. Okay, so we know this is now a critical value. So what occurs at critical values, or how we'll describe them? So in this case, the critical value, what you notice is the function is changing from decreasing, and then it starts increasing at the critical value. Okay, so it was decreasing, and then it came to a critical value, and then it started increasing. Okay, so that's something of note that happens that can happen at critical values. So then what we also have here is what's called the relative max or relative min. Okay. So let I be the domain of f. So we have f of c is what we call a relative minimum. If there exists within I an open interval we'll call I sub 1 containing c such that f of c is less than f of x, for all x in I1. What the heck does that mean? Okay, it's a little wordy for something that's pretty obvious, actually. If you have a graph that looks like this, okay, it kind of looks like an M here. Okay. Do you notice that this peak right here is a maximum value relative to values that are close around it? And then also this one here, here's another peak. Okay? It's a maximum value relative to the other values around it. And it might actually help. Let me just change this a little bit, this graph here. Suppose the graph looks like this. Sorry, I should have made this. Like neither one of these is the maximum value of the graph because the graph shoots up, way up here. But relative to the values around it, okay, they're peaks. So relative maxes occur at these peaks. Oh, sorry, this was a relative minimum, but I wrote relative max up here. Sorry about that. I did these backwards. My apologies. Relative max occurs at peaks. So what is this relative min that I read the definition for and made a little mistake here? But the relative min, okay, occurs. Do you see this little valley here? This valley? The turning point of the valley is a relative min because relative to the values that are close around it, it's the minimum value. Okay, but it's not the absolute minimum. Like neither is this valley here. Okay, because this graph goes all the way down here too. Okay, so relative mins occur at valleys. Okay, so when you have these peaks or these turning points where it's going, and look what happens here. The graph is increasing and then it goes decreasing. Okay, so that means that we hit a relative max. Then it's decreasing and then increasing. We hit a relative min. Okay, so relative to the values around it, it is a maximum or a minimum value. Okay, so just remember, minimums occur at these valleys of graphs where it's a valley, and relative maxes occur at these peaks or these other turning points here. All right, so the next thing we have here is that if a function f has a relative extreme value, f of c, so that's when I say relative extreme value, that's either a min or max value on an open interval, then c is a critical value. So notice here, even going back to our x squared, it had a valley. It has a valley here. This is a minimum. And the valley, the turning point of the valley occurred at a critical value. So what's going on here is you can find where relative min and max occur. Okay, either the peak of the mountain or the bottom of the valley, okay, because they occur at a critical value. Okay, so just so this is clear, for f of x is equal to x squared, f prime of x is equal to 2x, x is equal to 0 here was a critical value. What that means then is that 0, f of 0, this point is a relative max or relative min. Okay, all we know from this lecture that it's a minimum value here, okay? But, at least we know for some of the more complex problems you'll see in a little bit when I get to the other lectures that these critical values, okay, where the first derivative equals 0 or does not exist, they say, okay, you have a relative max or a relative min here. So now it becomes like, how do we determine if it's a relative max or a relative min? So this is what's called the first derivative test for relative extrema, okay? So for any continuous function f that has exactly one critical value c in an open interval, okay? So the first one, f has a relative min, okay? If at c, if the first derivative is less than 0 on a to c, and then it's positive on c to b. Okay, so that's a little confusing. So what that means is it's decreasing to the left of c and then increasing to the right. So what decreasing means, the function's going down, then it hits x is equal to c, so it's decreasing, and then after c, it starts increasing. Okay, so I promise this will make more sense when we actually get to some of the more complicated examples, and all this stuff will start making sense. But it's decreasing, and then it hits c, and then it starts increasing. Next, it has a relative maximum at c if f prime of x is greater than 0 on a to c and f prime of x is less than 0 on c to b. That is, f is increasing to the left of c and decreasing to the right of c. So you have this relative max. Okay, here's x is equal to c. The function will be increasing to the left of it, and then as soon as you get to c, it starts decreasing. So the only way it can go from increasing to decreasing is if that's a relative max. And it's the same here, right? Like decreasing and then increasing, it has to be a minimum. All right, so f has neither relative max or relative min if they're the same sign. So what I mean is if it goes, if there's a critical value and it goes increasing and then you hit the critical value and then it's still increasing. Or the same thing here. To the left of it, it's decreasing and then all of a sudden it's decreasing again. All right, let me end this first lecture before we get into some of the more complicated examples by showing you some visuals of this, because that always helps, okay? So look, here's this concept of a relative minimum. All right, you have this critical value at x is equal to c. To the left of it, the function is decreasing. Okay, so the sign of the first derivative is negative here. Okay, this is what I mean on this a to b, and then a to c, and then c to b. And then once you get past c, it's increasing and the sign of the first derivative is positive. Okay, so remember when it goes decreasing and then increasing, relative min. So the flip side here, okay, here's a critical value c. If the function is increasing, the sign of the first derivative is positive, and then once you get past this c, the function starts decreasing and the sign of the first derivative is negative, you have a relative max. Okay, so just remember, relative mins occur at valley, and a relative max is a peak. Here's an example of what it looks like when it's decreasing, decreasing, and then increasing and increasing. We'll actually talk about these with a little bit of analysis with the points of inflection in a later video. But for now, just this is what happens. It's decreasing, and then it's still decreasing. Or it's increasing, and then it's still increasing. Okay, that just means if it goes from decreasing to decreasing or increasing to increasing, it just means there's no relative maxima or relative minima. All right. I realize that a lot of these lectures, when you watch them, especially when they're introducing theories, can be a little confusing. Okay, I completely understand that. And so what will happen is we're going to do two examples where I'm going to do all these things. I'm going to find the derivative, critical values, intervals it's increasing and decreasing, and then determine relative extrema. So I'll do an example for this polynomial function, and then I'll show you what the graph looks like, and then I'll do one for this type of function next. So there'll be two videos. I'll break it up because these examples can be a little long.